We're going to talk about two more other special types of diodes before moving on to the next unit. The first we're going to talk about is a Schottky barrier diode. And so in a Schottky barrier diode, or just Schottky diode, what we do is we replace the p-type region with metal. So here in the left, we see where we would have had a p-type region, we now just have this metal. We still have our n-type region, and then our voltage and current markers are still the same. So our circuit symbol is a little bit different than our normal symbol for a diode. So we see over here on the right, we now have this triangle, but instead of just a line, we almost have this little S symbol to indicate that it's a Schottky diode. So the main difference between a Schottky diode and a p-n junction diode is that our Schottky diode is a majority carrier device. So remember, our p-n junction we said was a minority carrier device. And so what this means is if we're comparing to a p-n junction, so compared to p-n junction diode, our Schottky diode is going to have shorter switching times, so it can switch faster. So if we're dealing with high frequency applications, of course that is something that we are interested in. So shorter switching times. It's also going to have a higher reverse saturation current. So just to be really explicit, I'll say magnitude of reverse saturation current, because of course it's not getting positive. So we do have a higher reverse saturation current, which generally isn't ideal, but as always there are going to be trade-offs. And then we also have typically a lower cut-in voltage V gamma compared to our p-n junction diodes. And so typical values for Schottky diodes is going to be more in the 0.3, 0.4 volt range as opposed to our 0.6 to 0.7 for our p-n junction diodes. But again, keep in mind there's a lot of variability with that as we're changing materials as well. So one other thing which I've touched on a little bit before, you might be asking yourself, okay, we've replaced the metal, we've replaced our p-type region with a metal, so now this junction here is a metal contacting an n-type region. Well, of course, these sort of terminals to the external world are also typically going to be metal. So how do we make sure that's not a Schottky contact as well? So how do we know we're not making a Schottky junction on both sides of that n-type material? And so that's a really good question. And so the answer is that there are sort of two types of contacts that we can make. And for these contacts going to sort of external circuits or external devices, we want to make sure that those are ohmic contacts. And so that means that they are not rectifying, they're not preferentially conducting in one direction, as we have with this case here, with this junction between our metal and our n-type region. Some things that are going to affect whether a contact is a Schottky contact or an ohmic contact is the metal type, so we can use different types of metal. But it's also very important to prepare your surface in a certain way, so clean it, do various things, maybe terminate it with a certain element. All of these things are important to make sure we have our right contact. Because of course, if we do have, for instance, a Schottky contact here as well, then we're going to get some really interesting and unexpected behavior, which we don't want in our circuits. So the last type of sort of special diode we're going to talk about is a Zener diode. And so this one's kind of unique in that it's actually designed to operate in reverse bias. So our Zener diode is going to provide some specific voltage, specific breakdown voltage, negative VZ, where VZ is called our Zener voltage. So again, we're going to have a slightly different circuit symbol to identify our Zener diodes. We can see now, instead of a straight line on the end of our triangle, we have sort of this Z. It's again a little different just to distinguish it from our S for our Schottky diode. Another important thing to note is that the voltage here is defined differently than we've seen with all of the other diodes so far. So our positive has typically been over here on the side where the triangle is, but now it's on the opposite side. And again, the reason for that is this is built to be operated in our breakdown region. So our Zener diode is operated in our reverse bias, and more specifically in our breakdown. And it's done intentionally, and so the reason for that is we can then use that as a voltage reference. So used as voltage reference. And so we're going to look at some circuits later on, not just in this next chapter, but later on with some different configurations as far as how these Zener diodes can be useful. But let's say, for instance, we could design a Zener diode to have a breakdown voltage of -5 volts. Well, if we position that in parallel to something that we want to be at 5 volts, then that's a good way to sort of keep that at 5 volts without having it fluctuate too much. So that concludes this first unit. So again, in the next unit, we're going to get into some more specific diode circuits and look at various applications.